very pleased to welcome my ex-NASA colleague and good friend, Tim Menzies. Tim's done a lot of really cool work on using machine learning for different software engineering applications, and he's going to tell us everything he knows.
Thanks, John. Is the sound working here? Okay. So thank you, John, for that introduction. Thank you for coming to see me. It's a pleasure to be here at Google. I have a talk that's about 45 minutes. And given the video format, what I'd like to do is do the talk and take questions after, unless you see some gross error that you cannot accept, in which case, please interrupt. So we want to talk about learning defect predictors. This is work funded by the National Science Foundation of America. And recently, we're having a lot of interaction with the Turkish Scientific Research, Industrial Research Council, TÜBİTAK, and we'll talk about that. Every talk needs sound bites. What will you remember of this talk in a year's time? Well, let me give you some sound bites. Maybe you prefer these to your own. I'm going to say that something called static code features can be used to learn software quality predictors. They're surprisingly effective. But I'm going to say that they're kind of stupid. I'm going to say that they're a shallow well. And given our current generation of machine learners and the current sort of data we're getting about as much as we're going to get out of this source of information. And better learners and more data will not increase what we're learning from this source, unless we change the rules of the game. And the second half of the talk is some experiments where we change the rules of the game and we do much better than seen previously. Just some acknowledgements. West Virginia University, my colleague Boyan Čukić, numerous talented graduate students, the soft lab people at Turkey, Jeremy Greenwald, who used to be at Portland State and is now at MathWorks, National Science Foundation, and the Scientific and Technology Research Council of Turkey. And just to say the obvious, this is me talking, not the United States government or the country of Turkey. This is an empirical talk, so it's worthy to advertise the PROMIS conference on empirical software engineering. All the data sets I'm offering here are online at the PROMIS repository. And if you think you can do better than what I'm about to show you, I invite you to do so. And please come to the PROMIS conference. The motto of PROMIS is a repeatable, refutable, and improvable software engineering experiments. And if that's too pompous for you, there's a simpler motto: put up or shut up. If I produce a paper at PROMIS, I try to, when corporate permissions allow, to also produce the data that the paper was based on. And the PROMIS repository now contains 70+ data sets for common software engineering problems. And I encourage everybody I meet to contribute to PROMIS, either as data or as challenge problems or as papers. And our keynotes for PROMIS 2009, Barry Beam from USC and Brendan Murphy from Microsoft. So I hope to see you there. This talk is about defect prediction. I need to describe to you what defect prediction is. And I need to answer some open challenges on even the base value of even doing something as crazy as defect prediction. So parts 1 and 2 is stuff I'm sure many of you would have seen. Part 3 is something you may not have seen before. There's a bunch of new results talking about variance results and ceiling effects with these static code defect detectors. And they're the basis of my statement that these static code measures are a shallow well, and we've gone about as far as we can go with those, unless we change the rules of the game. And I'll talk about one very simple method for changing the rules of the game. We have some conclusions and references. The slides have all the references. I'll give a copy to John. Please email me or John Penix, and we'll send you that. So what is the problem? Well, the problem is blind spots. If you're a diligent driver and you're driving ahead and you're doing everything you can to avoid accidents, it doesn't matter how good you are. Because of the nature of the car, you have a blind spot. You can't see the cyclist in your blind spot. Driving a car is like software quality assurance. Infinite quality assurance is infinitely expensive. The mathematics of black box sampling with replacements on the board, and it shows us the number of tests required to achieve a certain level of confidence that we've found something with a certain error rate. And you can see the log expression at the top, and if I put confidence to 1, absolute assurance, the log, it just explodes. Because we can't test everything, it's standard practice for test engineers to skew their limited quality assurance budgets towards the things they think that matters. For example, it's quite standard to restrict model checking just to the kernel of the guidance system of a rocket. Now, if we're only going to look this way at A, B, C, D, what about that huge space of stuff we're not looking at? And what I want is some very fast method of sampling all the stuff I'm not looking at. The stuff behind. And I want these methods to reach over and tap me on the shoulder and say, look, I know you think that this is important over here, but there's something over here you really need to look at. And one cheap method, one fast method for generating these black box sampling devices is to do a little bit of machine learning. And I hesitate to offer Google, a lecture in data mining, but for one slide, we have a table of data, we have features, we have a class variable on the right-hand side, and we're trying to find combinations of the features that predict for the class variable. And there's any number of learners to do this, very simple methods, naive Bayes, statistical feature combination, Cohen's Ripper learner, the C4.5 decision tree learner, random forests. The motto of random forests is that if one decision tree is good, why not build 500? And many, many, many more besides. And these all output combinations of features that predict for a class. So what we're going to do is we're going to give these data miners descriptions of the code we're working with. And for this talk, we're going to give them very, very simple descriptions. We're going to take modules, and what a module is depends on your language. It's the smallest functional unit, a method, a file, a class, the smallest thing you deal with. We're going to describe them in terms of some very quick, cheap to collect static code features, lines of code, lines of comment, number of symbols inside those modules, something about the core graph inside that module. And we're going to join that log to defect log saying, have we seen defects in these modules? Once upon a time, we used to try to do bug severity and frequency, and then given the poverty of the data we've been working with, we're forced just to binaryize it, just say you're defective, yes or no. And the output of the defect predictor is a prediction that says on future code you are predicted to be defective if. Now, here are some samples of the static code features we're dealing with. The legendary McCabe measures on top, the cyclomatic V of G, famous, or should I say infamous. Lines of code measures, lines of code and comment, lines of executable. The Halstead measures, symbols, operators, operands. 2 plus 2 is 1 operator 2 and 2 operands. But Halstead also says we should count unique symbols. So 2 plus 2 and 2 is really 1 unique symbol. And there's a whole bunch of other numbers that Halstead defines down the bottom. And at this point you're saying these are pretty stupid, we can't learn much from these, I'll half agree with you. And you'll see what I mean as the talk progresses. Why learn defect predictors from static code measures? Well, it's useful, easy to use, and widely used. If you ask how good people are finding defects, the IEEE Metrics conference in 2002 had a panel and asked that question, and the wisdom of the panelists is that humans reading code find about 60% of the defects. This is actually perhaps slightly on the high side. A more careful study by David Raffo talking about a certain Pacific Northwest company reports that their defect detection methods found between 35 to 65% of the bugs with a mode of 50. And the static code measures I'm going to show you, we rock in at 70%, 80%, depending on the data set. And our methods are very fast to apply. It's seconds to learn the defect predictor, seconds to run it over tens of thousands of examples. And when we compare that to the time involved in manual inspection, it's much faster. If you're doing a Forest Shoal kind of inspection or a Fagan kind of inspection, they're saying 8 to 20 lines of code a minute. And if you've got a review team with multiple people, take that 8 to 20 lines of code per minute and multiply that by the number of people doing things, and you see that we have a much faster way with the static code measures. For these reasons, there are hundreds of research papers that have explored this, perhaps dating back as early as Porter and Shelby's 1990 paper. If anyone knows one earlier than that, I'd like to know where this idea first came from, but that's my earliest reference, Porter and Shelby, 1990. And I know large government contractors that won't trigger their Tiger teams to look at problems unless some sort of static code measure wakes up and says, this is a problem. Now, when I tell people I use static code measures, I get a couple of responses. One is, well, that's stupid. There's not much information in these static code measures, and I will half agree with that statement. They say, why use that? Why not use knowledge of the developers? How good are your people? How long have they been working with that code base? Why not use a history of runtime defects and do some sort of John Muser reliability engineering where you're talking about the trends of defects versus time? And, or why not use XYZ? And here are references to some very interesting papers that have used other kinds of measures and have achieved very interesting results. My reply is I use whatever is available, and that changes from site to site. And I dream of the day that one day I'll work for an organization where I can collect a lot of data in a consistent format over many projects over many years. Meanwhile, in the real world, let me show you the organization I've been working with for the last 10 years. This is a record of the NASA Software Independent Verification and Validation Facility. The left-hand side column shows the number of software projects they've been asked to review over time. And you can see that initially they weren't doing much, and by about 2003, they were reviewing about 42 projects a year. And these projects were very divergent, very different contractors, different goals. In the middle column, you can see some interesting features. Initially, it was all manned space flight systems, space shuttle. By the middle of that big bump in 2003, it was mostly unmanned. You can see that in 1996, there was a strange situation where to have IV&V work on your project, you had to give up some of your budget. And that was caused all sorts of political problems. And so there was this lack of information coming through. 2003, NASA reorganized that and said, we will fund IV&V from a central source. So IV&V became a free service to the projects, at which point the number of projects peaked and the information flow maxed out. 2005, different data was collected. 2007, the fashion changed, that stopped being collected. The right-hand column, you can see all the different organizational units that ran IV&V. Johnson at Texas, headquarters on the East Coast, NASA Ames down the road, Goddard Space Flight Center. And every time it changed organizational units, the databases changed, the information changed, et cetera, et cetera, et cetera. Not shown on this chart is all the organizational change that happened after the loss of the Columbia, all that massive reorganization. Not shown on this chart is the impact of George Bush's 2004 statement, we're going to the moon. And not shown on this chart is the layers and layers of subcontractors and subcontractors and sub-sub-subs. And here's me in the middle trying to collect information from this cauldron. This is not to say that this NASA site was somehow crazy or out of control. I know many commercial organizations with a faster pace of change than this. So instead of saying, what are the right features to learn quality predictors from, perhaps a better question is to ask, what are the features available right now? Now, if you can't control the data collection, but you were doing what I was doing, which is after the data is collected, do what you can. And you're talking about other groups' agile or outsourced projects or open source projects or layers of subcontractors. You do what you can with what you can get. And up to now, the thing I've been most able to get is the source code. So that's why I work on static code features for defect prediction. So that's a statement that I have to work on that code base. That's not a statement that if I do that, I learn anything that's useful. What is the value of learning quality predictors just from lines of code and comment, just from symbol counts? Okay, well, I mean, aren't these static code measures kind of stupid? There's any number of papers that will say so. There's papers that say that the infamous McCabe V of G is just a simple synonym for lines of code. It's highly correlated to lines of code. There are worthy papers that say things like, for a large class of software, V of G is no more than a proxy, and in many cases outperformed by lines of code. So aren't static code features stupid? Well, if they were stupid, they wouldn't do very well. The performance figures would be rather low. And if they were really, really stupid, there'd be nothing you could learn from one project and apply to another. There'd be no signal in what they're telling us. So let's try an experiment. Let's take data, radically different software projects. In this experiment, we had 4 NASA flight systems. We had 3 NASA ground systems. And just because we could, we went to Turkey to some white good manufacturers, people doing washing machine software. And we started learning from one group and applying to another. Now, before I tell you what happens, let's just point out that at NASA, there's any number of people that will tell you that ground systems are fundamentally different to flight systems. You can't learn one from another, or there's not much you can learn from one and apply to another. And certainly when I tell the NASA people that I'm building defect predictors for their aerospace systems from Turkish white good manufacturers, they say, well, what? And if we look at the processes involved in here, like the Turkish developers, talented people, but and a lot of their work is hero-based programming, you know, single groups, powering through, whereas the NASA stuff does large software process stuff. And you see a divergent range of languages, C++, Java, C. The idea that you can learn anything from part of this group and apply it to another, especially from something as stupid as static code measures, that would seem to follow. Well, before I tell you what happens, the performance measures, I have to digress a bit and just talk about performance measures. Again, I'm sort of reluctant to do a data mining tutorial at Google, but just in case there's other people watching this video, let us to say that A, B, C, D are the true positives, the false negatives, the false positives and true positives respectively found by a binary detector, and with these letters, we can define the recall, the false alarm rate, precision, accuracy. The neg-pos ratio is important. It tells us the size of the target. If only 10% of your data, of your training set has defective modules, your neg-pos ratio is 10. And it turns out that for skewed data sets with large neg-pos ratios, certain common measures you just don't want to do. For example, have you ever thought that you could be accurate and miss everything? Accuracy, yeah, in the situations for large neg-pos ratios, does not predict for probability of detection. Here's an example where we had round about 500 modules, and on the left-hand column shows round about 400 examples where there weren't defects, and the right-hand column shows about 100 examples where there were defects. The first row shows where the detector was silent, and the second row shows where our static code defect predictor triggered and said, I predict a defect. Now what you'll notice here, if you apply the equations, is your accuracy and false alarm rate are looking pretty good. 83% accuracy and 5% false alarm rate. I need to cough. Are we going to just... Thank you. Okay, so notice that our accuracy is 83%, which is good. Our false alarm rate is 5%, and our probability of detection is 37%. So just beware in unbalanced data sets using measures like accuracy. End digression, let's go back to our experiment. Let's learn static code predictors using a naive Bayes classifier. Why use something as simple as naive Bayes? Well, we'll get back to that in a second. And we'll do two experiments. We'll do a round robin and a self-learning experiment. In the round robin experiment, we'll train on them and test on me. So in a round robin experiment, you have 10 data sets. One of them you'll test on and you'll train on the remaining 9. In a self-experiment, you'll take one data set, learn on 90% of that data, and test on the remaining 10%. Now, if you do this round robin experiment where everyone's defects is predicted by everyone else's code, you get a 94% probability detection of finding the bugs. 94%. But before you get too excited about that, please note in red the 68% false alarm rate. So if I rush out to a huge crowd of people and ask their opinion, yeah, they're going to tell me when I'm going to have a problem, but they're going to tell me lots of irrelevancies as well. So beware surfing the crowd. In the self-experiments on line 2, I'm just going to learn from me and test on me. And I get detection rates of about 75% and false alarm rates of 29%. And this is adequate for the statistical purpose of controlling a large group of programmers trying to maximize the amount of time of these QA teams trying to work out whether what the detectors triggered on was actually faulty. Now, it turns out with a very simple nearest neighbor trick, we can turn the round robin stuff into useful stuff. It turns out we can learn from the crowd in a very simple way. In the last line is a round robin experiment, but for every test instance, we found the case nearest neighbors in the training set. And recall here that the test is from, say, a Turkish white good manufacturer, and the training set is NASA Flight, NASA Ground, and other Turkish systems. And with that simple nearest neighbor filter, we get about a 69% detection rate and a 27% false alarm rate, which is adequate for the purposes of controlling large populations of QA people. So from this experiment, we can say it's best to learn from local data. However, it is possible to use imported data, but make sure you do some relevancy filtering on the imported data. So if you don't have data, start local data collection. And meanwhile, use imported data filtered using nearest neighbor. And I recommend to you the Promise repository, the data up there. There's enough there to get started about learning defect detectors. Now, a question that arises when I show people this slide is they say, well, okay, how much data is needed to build my local defect detectors? When do I switch from using imported data to local? And we'll get back to that several times in this talk, how much data is enough to learn these defect predictors. Now, here are some results that you may not have seen. For many of you, this has been, data mining 101. But let's talk about several questions. What are the best static code measures to learn from? Well, it turns out that there isn't a best set. Let's do a feature subset selection experiment. If I have a bunch of features and they have a certain performance, let's add in another feature, grow the set, and see if the performance improves. And we'll do that experiment until the performance no longer improves. And we'll do it the right way. We'll do, a greedy search with an horizon of 5, 5 lives before you die. And our target learner inside this wrapper will be a naive Bayes. And the table on the left shows 6 data sets and the index of the features selected. Now, in these experiments, we had 42 static code measures. And please note that in the 9 experiments shown on the left-hand side table, we never needed more than 3 features. But please notice that we found different features all the time, nearly all the time. Like the dataset PC1 needed features 3, 35, and 37. The dataset MW1 needed 23, 31, and feature 35. And we can go through that list if you want, but the tallies are on the right-hand side. Feature 1 was used twice, feature 3 was used twice, no feature was used all the time, no feature was used in the majority of cases. There's 9 data sets on the left, you have to appear 5 times or more to be in the majority. So what's going on? Why isn't there a best data source to learn from? Well, let me introduce you to the feature information variance effect. This is an experiment where 10 times we take 90% of the data, and then we use something like the Wecker's information gain to ask, what's the information content of this attribute? Now, if you look at the sorry, I'm confusing the terms here. I should consistently say features all the way through this talk, and attributes appears on the x-axis, so I apologize for that. If you look at the information gain over 10 90% samples, what you see is there is a large number of features on the left-hand side on top of a plateau. This is the space of possible good detectors, and they have a variance. Can you see the error bars showing the variance over the experiment? So what we have here is a whole bunch of weak indicators on top of a mountaintop saying, I'm useful, I'm useful. So what I want to offer you is that these static code measures are a pretty dumb way to characterize code. They're a weak indicator. But if we take 3, 4, 5 of them in combination, if they all point in a certain direction, you can start saying, yes, I actually have a bug. And so, by the way, if anyone ever offers you V of G greater than 10 as a detector, please point out to them that the empirical basis for that measure is kind of weak. Seemingly minor changes in your sampling policy would mean different detectors appear at the top of that plateau. In your cross-validations, for example, the way you set up your random number generator will mean different predictors will look better than others. Another question people ask me is, what's the best data miner to use? And these are some recent results describing a ceiling effect. And you'll recall that a ceiling effect is an inherent upper bound on the performance of some device. The left-hand side is some experiments from WVU grad students. The right-hand side is a recent paper by Lessman et al. In TSE July 2008. Now, in round about the middle of 2006, I did perhaps one of the largest defect prediction studies to date on NASA data, and I achieved a certain level of performance. And I've been unable to improve that performance since 2006. Now, if you look at these results, on the left-hand side, you've got 9 different learners, and you've got quartile charts, and 6 of those 9 are very similar high values. I mean, statistically, boosting actually does best. Naive Bayes does second best, and it is statistically different to boosting, but given the simplicity of boosting and the computational cost, given the simplicity of naive Bayes and the computational cost of boosting, I can't recommend boosting over naive Bayes. I should say what the, just don't ask yet what's the y-axis, what's the performance measure. I'll get back to that. For the same performance measure and for many of the same data sets, Lessman et al. Report a similar ceiling effect. Can you see just here a vertical dashed line? Okay, well, these, and can you see that random forests generates the highest rank performance for these data sets? But can you also see that the rank of random forests has a large variance? Now, if you do the stats, and Lessman does the stats correctly in my view, 14 of these 19 data sets are statistically indistinguishable from the top ranked person. So these 14 here are the same. And here's my beloved naive Bayes just here. C4.5 is also in this as good as the best just here, even though over here a Java port of C4.5 is one of the worst. So there's some issues about the experimental methods and why we're not getting stable results. But the general message here is that if you run a whole bunch of learners on these defect predictors, many of them will produce the same results. Now I have to tell you what the evaluation bias was here. Both these people used an area under the curve of a probability of detection and probability of false alarm graph. And those of you who know these sort of ROC curves, and I'll show you some examples in a minute, if you do your cross-validations or random samples of the data and multiple learners, you'll get multiple points sitting on a PD versus PF plot. And the area under the curve is a common measure for performance. And on that measure, lots of learners perform about the same. Well, perhaps we need more data. Maybe it's not the learning we need more data. Well, here are some studies on 2 data sets. The effect I'm about to report occurs in many more data sets. I just don't have room or time to go through them. And this is all stuff from the Promise repository. If you want to check this, please do so. The top results are picking 100 modules at random, training on 100, 200, 300, and then testing on another 100 not used during training. That's the random sampling one. The bottom one is micro-sampling, where you pick n defective and n non-defective at random and learn from that. And in the bottom set, we set n to 25, 50, 75, and then we train on 25 examples not used during, then we test on 25 examples not used during training. And the effect is the same in both. Statistically, there's no improvement in the random sampling over about 100 instances, and there's no improvement in the micro-sampling over about 50 instances, half-half defective, non-defective. Now that's kind of good news, but it may mean that a whole bunch of my graduate students aren't going to finish. We're not doing better with better learners, we're not doing better with more data, and so people like Lessman will say the importance of the learner is less than generally assumed, and practitioners are free to choose from a broad set of candidate models when building defect predictors, which sounds like the end of the line. It's all over, there's nothing left to do. Well, given that it's only halfway through the talk, you can kind of guess what's going to happen next. We're going to change the rules of the game, and when we change the rules of the game, this ceiling effect changes in an interesting way. So let's change the rules of the game. These learners have an evaluation bias, and depending on your business, you prefer different learners. So for example, consider this PD versus PF graph. This is one of these ROC curves, receiver operator characteristic curves, and recall that we measured the performance of a learner by the area under the curve, and we build different models using subsets of the data. And the false alarm rate is along the bottom, and the probability of detection is along the y-axis, and the sweet spot is 100% detection, 0 false alarm, which is up top left. And if you look at the characteristic curve of learners, it bows up towards the sweet spot and doesn't quite get there. The line PF equals PD is where your probability of detection equals your probability of false alarm, and we call that the no information line. And the negative curve, if you have a learner that's running down that negative space, typically you can negate something and it throws itself up into that space. So really, the space of learners is the curve on top. Now in that curve on top, there's 2 interesting regions. There's a risk-adverse region where you want high PDs. You will accept anything as long as you get high PDs. And given the shape of this curve, the only way to get high PDs is also to have high PFs. Consider airplane flight and pregnancy. I flew here and I stood in line, and sometimes I have to handle some impertinent questions from security guards, and I'm willing to put up with that. I'm willing to put up with a false alarm rate so that when I get on the plane, any bomb has been detected before I get on the plane. Morning sickness. Morning sickness is that condition where the body is suspicious about stomach contents and removes them. It wears a high false alarm rate in order to preserve the life of the fetus. So these are risk-adverse situations where you want to choose learners that drive you into the high PD and high PF region. There are other business situations where you don't want to waste your money chasing false alarms, and you're willing to wear medium to low probabilities of detection as long as you don't have any false alarms. So that's the risk-cost adverse region just there. And so rather than assessing these learners on some uniform evaluation criteria, instead, let's talk about your business and say, what's your evaluation criteria? Now, a Schlerman-Briand offer an evaluation criteria that's so different to what's been explored before that we're going to see what happens when we impose that. And what our Schlerman-Briand say is that my probability of detection had better be greater than the effort involved in processing these examples. The detectors trigger on a code base, and let's say you trigger on 20% of the code base. According to Schlerman-Briand, you want to have more than 20% of the defects in that 20% of the code base that you've triggered on. So in their preferred criteria, the PD has to be greater than the effort. All right, so let's talk about tuning learners to the business criteria. Let's talk about evaluation-aware learners. Every learner has a bunch of biases. There's a sample bias. What data are you learning from? There is a search bias S, and there's an evaluation bias E. And in the search bias for things like decision tree learning is, which is the next best attribute to split on? And for those of you who know this stuff, information gain is the standard search bias used in C4.5. And then once the model is generated, it goes out to the business users who assess them. And I hope by now I've convinced you that for data sets with high neg-pods ratios, you don't use accuracy, but you might use PD or PF, or you might use the Schlerman-Briand criteria. Now, I believe, in all my reading of the defect prediction literature, I believe the following is true. Typically, the search criteria used to build the theories is different to the evaluation criteria used to assess the learnt theory. Now, having said that, the natural next question is, what happens if you make the search criteria the same as the evaluation criteria? You start as you mean to go on, you import the business context into the inner loop of the learner. What changes? Now, my grad student, Zach Milton, explored that in a learner called Which. And Which is incredibly simple. And for those of you who know AI search, we can talk about some of its interesting features. But it's very easy to describe. Firstly, discretize all the numeric ranges. Secondly, score all those ranges according to the evaluation criteria and sort them onto a stack. Thirdly, pick 2 entries from that stack, favoring things towards the top of stack. Now you've picked 2 things that seem good according to E, combine them, put them back on the stack and search them, sort them into their right space. So next time when you go around to pick 2 ideas, you're picking things near the top of stack. Now the right-hand side plot shows for UCI data sets the score on top of stack. And the interesting feature is that after a small number of picks, 20, the top of stack score usually stabilizes. And in one case marked in A, after 110 picks, we did better. And we'll just double that, and we'll run Which for 200 picks. That's the Which learner. Now notice that there's no search criteria. There's no separate search criteria S in Which. Instead, we can take the evaluation criteria used by the business and we can wire it into the guts of Which. When you compile Which, you actually write 3 lines of C saying, what is my evaluation criteria? Now, certainly there are other methods that could bias their learning in this way. I think it would be natural to go to decision tree learners and adjust the decision split criteria according to this sort of thing. I'm not sure that cost-sensitive learning or rock ensemble combination is useful in this context. You can do your cross vals and you can have as many learners as you like learning optimizations of area under the PDPF curve, and I'm not sure that any combination of those will win on effort versus PD, for example. But we use which for the following experiments. Well, firstly, because we built it. And secondly, this early termination of the learning shown top right suggests that which could be useful in the future for stochastic real-time, anytime learning. But it doesn't really matter whether we use which or some variant of the bottom three methods. All we're going to show you is what happens is when we tune the learner to the evaluation criteria. We remove this separation from the search criteria to the evaluation criteria. And what happens is, okay, so let's talk again about Schlumann-Brion's evaluation bias. They say if you're a budget-conscious team, and if X% of the modules are predicted to be faulty by some predictor, and they contain less than X% of the defects, then they would say this defect predictor is not useful. They want probability of detection greater than effort. So on the right-hand side curve, you can see the percent of the code base on the x-axis that the detector triggers on. The y-axis is the probability of detection. And we can see some interesting curves on this plot. The minimum line where PD equals PF, this is the minimum bound. According to Brion and Schlumm, has to be above that bound. The best curve is interesting. We can offer an upper bound of performance of this device. Ganesh Karu and his colleagues at University of Baltimore, Maryland County have pretty much convinced me that smaller modules contain a disproportionate number of errors. They offer the following inspection policy. Take all the modules you're looking at, sort them by size, and look at the smallest one first. And there's interesting reasons why that actually works, and we can talk about that if you're interested. But supposing some omnipotent oracle reaches down and says, I am triggering on just the defective modules. And you take those modules and sort them by increasing size, you get the best curve shown there. And at the point of A equals 30, a 30% of the code base is in modules containing defects. We can't do better than best. Our learners will not do better than best. And what we'll do is we'll express our learners as the ratio of their area under their performance curve to the area under the best curve. So the performance results I'm about to show you are percentages of best. Now, a few things happen with that fraction. Firstly, you may ask how we operationalize the y-axis. How do we really know we've found something? Because the detectors trigger and they have a false alarm rate, right? So we'll assume there's a secondary process that looks at what we triggered on and says that's actually an error. It could be a human inspection process. And let's say that secondary process is delta % effective. That delta is common to all the curves. By dividing the area under one curve to the other, we actually divide that away. And so now we can assess any defect prediction method regardless of the downstream final check. And just to give the game away, can you see the manual curve there? That's what happens when we apply Ganesh Karu's rig on our data sets. We do better than PD greater than effort. And we have learners, you can see the bad curve there, that actually do worse than manual methods. And embarrassingly, one of the learners I've been telling people to use for years actually does worse than Ganesh Karu's manual rule for inspection. Happily, we do have good learners that work better than manual methods and approach a large percentage of the best. So let's look at some results. So we're going to go back to those NASA and Turkish Whitegood data sets from the PROMIS repository. We're going to do 10 random orderings of the data and a 3-way cross-val. It's standard practice to repeat these experiments. I don't need to tell you folks this. It's standard practice to repeat the learning n times, repeating the ordering to isolate you from ordering effects. In the plot in the middle, the rank comparing each row is computed using firstly a Mann-Whitney U-test to see whether your distribution is different to the next guy, and then you get a higher rank if you are different and your median value is higher. The performance scores here are the percentage area under the best curve. We have various learners, which Micro 20, Naive Bayes, Ganesh's manual method, C4.5, and Cohen's Ripper method ported to Java in the Weka called JRIP. Micro 20 is a variant of which, where we do this micro sampling thing, where we learn on 20 defective modules and 20 non-defective modules. And recall here that we are trying to optimize for area under the PD versus PD versus effort curve, and the learners that have been tuned to that criteria do best, which and micro. And the learners which were developed historically to optimize for accuracy, C4.5 and Ripper, do worst, do very badly, in fact. Now, naive Bayes, which is this method I've been saying is good enough and it's easy to do, does no better than manual. Does no better than manual. So please, if you have a certain paper of mine on the shelf, please just cross out certain lines in the conclusion. And the micro-sampling method that only learns from 40 examples does nearly as well as which that learns on many more examples. Now, this is results from one data set. We have papers repeating these results on many more samples, again from the PROMIS repository, and the pattern I've just offered you repeats across all those data sets. So we have more evidence for the shallow well. After about 40 examples of it and not it, we do as well as anything else. We do better than manual, thankfully, and a whole bunch of learners used quite standard in this field do very bad when assessed on effort versus PD. Okay, so what are we saying here? But why does it work? That's a question. I don't have any answer to this question. I've just shown you that we have a ceiling effect based on area under the curve, PDPF. And if we change the rules of the game and do area under the curve of PD versus effort expressed as a ratio of best, we can do better. But fundamentally, why does it work? Well, I submit to you that there's another related question. Why does any information retrieval method work on any technical corpus? Do you folks know Andy Marcus's work on concept location? Like you're changing a piece of the code and you want to know where else to go look to find related stuff to change. That's a common maintenance task. Andy solves that using some information retrieval methods. He doesn't do deep semantic parsers of the code. He does simple symbol counts of the methods. And this simple information retrieval method for a large enough corpus lets him find related concepts to what you're doing right now. Why does that work? Why do these stupid static code measures work? What's going on? Is there some constraint which when we work on our compilers, our languages, our target domains, is there something about human short-term memory which means that we don't work across some wide plane of possible behaviors? We actually are somehow constrained to a very narrow valley. And in that narrow valley, very simple symbol count methods like the one I've been showing you here are enough to offer you guideposts that point you in the right direction down the very narrow valley of behavior we actually do. What is this invisible hand that is constraining the work, our technical work, such that these simple methods work? I don't have answers to that question, but I hope to in 5 to 10 years' time. If you want to know what will I be doing for the next decade of my life, it's that last question. What is the invisible hand that makes all this work possible? But these are some questions I do have answers to. Are defect predictors useful? Well, if you're only going to build these defect predictors, it's not useful. But if you're going to use them as a way to control when you trigger much more expensive QA methods, when you bring back the guru from her 6-month holiday and say, we really need you to work on this thing for a month, when you wake up the model checking, when you wake up the more expensive methods, yes, these methods are a good way to very quickly sample a large space of code that you're currently not focusing on and finding what else you should be looking at. Are these defect predictors general? Well, yeah, I mean, this is strange to say, but I can go to NASA flight systems and learn a theory that's relevant to Turkish white goods and vice versa. That's pretty strange. Is it best to use other people's data? Well, no, it's actually best to use local data. But you don't need much. Dozens to under 100 examples, depending on whether you're doing micro-sampling or random sampling. And that's because these static code measures don't contain much information and we can scoop them out pretty easily. Which learner is best for building defect predictors? Well, if you're maximizing for area under the curve of PDPF, you have many choices. But if you have another evaluation bias, it might not be best to use the traditional machine learning set that's been optimized for accuracy or PDPF. It might actually be better to tune your learner to the evaluation criteria that its models will be assessed to. And which was an example of how simple that tuning could be, and there are certainly other ways to do that. What are the best static code features to learn on? Well, that's the wrong question. Best turns out to be a domain-specific construct. And my advice to you is to collect everything that's readily and cheaply available and throw it at a learner and see what happens. Which brings me to the reason that I'm at Google today. Apart from visiting your wonderful campus, we have an NSF project where we're trying to take seriously this idea of local knowledge. And what I'm talking to many companies about whether we can find people willing to work on some rig where human expertise and data mining get together, and maybe one surpasses the other. We've seen above that the best features are dataset dependent, and we call that the feature information variance effect. And we have many examples where if you go to a site and say, well, there's a bug, local knowledge wakes up and tells you a different story. One example from Microsoft, some data mining colleagues of mine found a bug in a certain Windows API. And the Windows team said, it doesn't matter. What do you mean it doesn't matter? Well, for contractual reasons, we have to maintain that for back compatibility to Windows 3.0. But nobody ever uses that API. Now, that sort of local knowledge is important to know. You don't want to spend time fixing a bug no one cares about. And we've seen that we can do pretty good learning on dozens to under 100 examples. Now, one of the reasons to do data mining is that the data space is so large that humans fall asleep working through it. If we're down to dozens to under 100 examples to learn adequate theories, maybe we can augment or maybe even replace data mining with human-in-the-loop case-based reasoning. So if you think that your domain expertise is better than my static code measures, I'd really like to talk to you about trying to set up some rig where we can work together. And happily, given this is the start of the NSF project, we have about a 2.5-year window to work on this, so we can talk about baby steps and then working on to more elaborate things down the way. So this is the end of the talk. I've made the case that static code features can be used to build software quality predictors. They shouldn't be by any means the only thing that you do, but they can be the gatekeeper that controls whether you apply more expensive methods down the way. But these static code measures are a shallow well. It's very easy to get to the bottom. We are not extracting more information with better learners, with more data. And in fact, after less than 100 examples, and sometimes even dozens of examples, we're doing as well as anything else. I suspect we're not, if we stay with the traditional rules of the game, area under the curve, PDPF, we're not going to do better. And so I'm advising we change the rules of the game. Let's build learners specific to the business criteria. Barry Bean's been talking a lot recently about value-based software engineering, where instead of saying, let's remove all defects at all costs, let's start saying, well, wait a minute, we have to balance that against things like we have to get it to the market sooner. So we might trade off getting it to the market with a few more defects as long as we can do some market-leading work. So let's talk about my advice to you is the way to improve these learners is not to look at the data and not to look at the machine learning. It's to look at the business, to look at the domain expertise and see if we can push those into the learner. And so I'm here today to see whether we can do things where we augment data mining with human-in-the-loop processing. Okay, so how long do we have for questions, John? 5, 10 minutes? Okay, so we have time for questions. So any questions or comments?
Well, actually, one comment I should mention. So we've got a room booked for discussion after lunch. I'm in Madrid. So anybody who wants to get involved in a longer discussion, go down to Charlie's, get lunch, and then meet us in the Madrid room. We've got that for like another 2 hours.
Excellent.
To do a more in-depth discussion. And we should be able to VC in if you want to come in remotely.
So that'd be quite exciting. We can really get to the details. For those who have meetings this afternoon, any questions from the people?
So did you say, did I hear it correctly, that the smaller the method or the class or whatever, the higher the probability of error in that?
So the question was, do I believe that smaller methods contain more errors? Yeah, I do. There's probably, can I expand or do you want to throw? Oh, sure. Supposing you've got, well, firstly, it's an empirical observation. And I've seen it in enough data sets to really believe it. If I can go back, if that thesis was wrong, then on this experimental rig, the manual curve would be shaped the other way. So I actually took out of this talk a comparison of manual up versus manual down. And in manual up, we run through and look for bugs in the smallest first, and in manual down, we do the result. And I can tell you that in 8 of the 10 data sets I've looked at, manual up beats manual down. And there's some very exciting papers by Ganesh describing this work. Empirical Software Engineering, October 2008, very nice paper. Now, why? Why? Well, consider some IDE, some object framework where what you're doing is you're not building large systems, but you're building lots and lots of tiny subclasses in many places across the space. So most of the work is in the upper levels of the framework, and you're providing lots of small things. And so your business concept, your design, has now been chopped up and spread like matchsticks across the code base. And in that rig, it's entirely feasible to me that smaller has got more errors.
Just going to comment, I looked at one of the data sets, the KC3 Java code.
Yes.
And in that case, most of the bugs were in large files, large modules.
Let me pull up the data I've got, and I'm trying to see whether KC3 was.
Well, so here's.
But now there was a question at the back. I don't want to cut anyone else.
Yeah, I'll work on it later.
I just was wondering if this included people type data, like how long it took someone to type a note in,
Now,
non-statistical type things.
So the question is there more information out there than the static code measures, things like developers, effort that went in by people?
Not personality type things, just how long it took to type it in.
Well, now, people with epilepsy, please don't watch. So in this work, no. This work was only based on static code measures because I made the case that sometimes if you're in a very dynamic organization with many subcontractors, you can't get that level of granularity. Now, I refer you to the first reference, a very nice ICSI 2008 paper that does explore exactly that issue. And I also refer you to Tom Ostran and Elaine Weiker's October ESE article where they ask, do too many cooks spoil the broth? And they ask whether bigger teams have more bugs than smaller teams, and they actually find no evidence for that. So does that answer your question, sir? And I shut you off.
No, that's fine. And I'll be talking to you afterwards.
Yep. Okay, other questions or comments? Any questions from VPN? Nope. Okay, well, thank you very much.